We're going to now look at some examples where we are going to state where our function is discontinuous and then state the type of discontinuity. In our first example, we are going to be looking at this graph. There is a lot to that graph. I think the best way to approach this problem is to start looking at this graph and see where it is discontinuous, and we'll start looking at the points on the left and then move to the points on the right. The first point that we're going to look at is x is equal to minus 2. At x is equal to minus 2, the function exists and the limit exists. However, these two values are not the same. So we're going to say that at x is equal to minus 2, we have what's called a removable discontinuity. It is not a jump discontinuity because when we have a jump discontinuity, the value starts at one value, goes to the next value, and then continues on from that value. With this one, our function only jumps at a single point. So it's called a removable discontinuity. Let's now look at our next x value, and that is x is equal to 2. Notice at x is equal to 2, our function is defined. However, the limit from the left is different than the limit from the right. And that tells us that we have a jump discontinuity. At x is equal to 2, let's write down that we have a jump discontinuity. Now let's look at what's happening when x is equal to 4. Our function is not defined at x is equal to 4, and our limit from the left is going to infinity, and our limit from the right is going to infinity. So at x is equal to 4, we have what's called an infinite discontinuity. Now let's look at our last point. That is at point 6. You might want to pause the video and see if you can determine what type of discontinuity we have here. Our function is defined at x is equal to 6, but the limit from the left does not equal the limit from the right. And that means just like when x is equal to 2, we have a jump discontinuity. So we'll write down x is equal to 6. We have a jump discontinuity. Let's now look at our second example. In our second example, we see that the function is defined at x is equal to 1. And to determine the type of discontinuity, we need to understand better what's happening in the region around x is equal to 1. So let's look at the limit as x approaches 1 from the left of 1 over x minus 1. This is approximately 1 divided by 1 from the left minus 1. So this is approximately 1 divided by a number like 0.99 minus 1. So this is going to be 0 from the left, and that's going to be minus infinity. Now let's look at the limit as x approaches 1 from the right. This one's easier. This is 1 over x minus 1. This is approximately 1 divided by 1 from the right minus 1. Think of this as 1.0001 minus 1. So this is 1 divided by 0 from the right. And this is positive infinity. Because our limits are infinite, we have an infinite discontinuity at x is equal to 1. So let's write down infinite discontinuity. I'm just going to abbreviate that at x is equal to 1. Let's go ahead and let's graph this just so that we can better understand it and see what it looks like. We have an infinite discontinuity at x is equal to 1. So we'll put a vertical asymptote there. And then at 1, our function is equal to 2. So we'll put a closed circle here. As we approach 1 from the left, we're going down to negative infinity. So our function's going to look like this. And as we approach 1 from the right, it's going to go up to positive infinity. Later on in this course, we're going to be talking about horizontal asymptotes, which we really need, honestly, to be able to understand this graph a little bit better. But for now, I just wanted you to see the graph so that you can see what it looks like when we have an infinite discontinuity. Let's now look at example 3. This one is a little bit more complicated, but just like our second example, our function is defined at x is equal to 1, and now we have to figure out what's going on at a region near 1. Let's take our complicated function when x is not equal to 1 and see if we can maybe factor it. Let's take x squared minus x, all divided by x squared minus 1. We can definitely factor it. In the top, let's pull out an x, so we have an x minus 1. And in the denominator, we can factor that as x plus 1 and x minus 1. Now let's notice that these two terms cancel out, and we can write this as x all divided by x plus 1. Because we canceled out an x minus 1, what we can do is we can take x minus 1, set it equal to 0, and solve for x, and we get x is equal to 1. This means at x is equal to 1, we have what's called a removable discontinuity because we were able to remove that from our function. Now let's look at the function that we have left. Notice that there is an x plus 1 in the denominator. Let's take that and let's set that equal to 0. And that gives us x is equal to minus 1. When x is equal to minus 1, our denominator is going to go to 0. So our function is going to go to infinity and also to minus infinity. Let's go down here to the bottom and write down then at x is equal to negative 1, we have an infinite discontinuity. And I'm going to go ahead and I'm going to highlight these answers. We have a removable at x is equal to 1, and we have an infinite discontinuity at x is equal to minus 1. Let's go ahead and let's graph this function just so that we can better understand this. At negative 1, we have an infinite. So that means we're going to have an asymptote there. Our function actually has a horizontal asymptote at y is equal to 1. Again, there's no way that you would know that at this point. Just take my word for it. And then we have on the right-hand side of our asymptote, our function's going to go down like this. It does pass through the origin, and it's going to go over like this. And then at x is equal to 1, it's defined to be 1, so we're going to put a closed circle there. And we're going to put an open circle right there. So you can see from the graph, we have an infinite discontinuity at x is equal to minus 1 and a removable discontinuity at x is equal to 1. Let's now look at our fourth example. This example is a piecewise function, so we're going to start by looking at the limit of this function as we approach 1 from the left and from the right. Let's first look at the limit of f of x as x approaches 1 from the left. That's right here, so we're going to look at that piece right there. So this is the limit as x approaches 1 from the left of 1 plus x squared. Plug in x is 1, so we just end up with 2. Now let's look at our right-hand limit. The limit as x approaches 1 from the right of f of x is the limit as x approaches 1 from the right of 4 minus x. Now we're grabbing this piece, plugging in x is 1, and we end up with 3. Notice that the limit from the left is not equal to the limit from the right, and it doesn't go to infinity, so this tells us that we are going to have a jump discontinuity. At x is equal to 1. Let me graph this for you just so that you can see this better. When x is equal to 1, we found that our function is equal to 3. So I'm going to put a closed circle right here. We'll mark this point 1. To the right of 1, our function is 4 minus x. That means it is going to have a slope of -1, and it's going to look like this. If we look at the first piece in our function, when x is less than 1, we plug in 1, we see that we got 2. So we're going to have an open circle here at 2. And then our first function is a parabola, and it's going to be shaped like this. Don't stress about the graphs for now. I just want you to see the graph so that you can see that we do have a jump discontinuity at x is equal to 1.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.